is Prof from the MIT, and she will talk about it's different. Conformally invariant growing mechanism in CLE4.
Thank you for the introduction. It's my great honor to give a talk at the Isaac Newton Institute. Today my topic is on the conformal invariant growing mechanism on CLE4. My talk will be divided into four parts. The first part is the background on SLE, CLE, and Gaussian free field. The second part is on the growing mechanism on CLE4. And the third part is about the coupling between Gaussian free field and the CLE4. And the fourth part is the outlook. Okay, we start with the introduction to SLE curve. You have already seen SLE in the last 2 weeks lecture, but here I will recall it briefly. So SLE curve is a random fractal curve in simply connected domain from one boundary point to another boundary point. It is introduced by Odette Schramm as the candidate for the scaling limit of discrete models. So it is a random curve satisfies these two properties. The first property is conformal invariance. Suppose we have the curve in D from A to B. Phi is a conformal map. Then the image of this curve under phi should have the same law as that curve in phi D from phi A to phi B. Second, the domain marker property. Suppose we have the curve in D from A to B. Given the first part of the curve, the future part of the curve have the same law as the curve in the remaining region from the tip to the end point. Here I have two remarks. The first remark is the the domain marker property is a natural property from discrete models. So let us consider the simplest example. We have a region D. We have discrete lattice inside this D, and we have site population. So at each vertex, we are black or red with equal probability 1/2. We fix two boundary points, A and B, and we require all the boundary points on this part to be white, and all boundary points on this part to be red. Then we sample independent white or red with equal probability 1/2 inside at each vertex. Then we will see that there is an interface from A to B. Separate white from red. So this is the object we want to study. So this is in the discrete lattice. And we want to see whether this discrete lattice, after property normalized, this curve converts to a continuous curve. So here, before we look at the limit, let us see this interface. If we move along this interface and stop somewhere, so suppose we know everything up to this interface here, we can see that the future part of the interface has the same law as the interface for critical population in the remaining region. So this is the discrete version of domain marker property. And when we try to study the scaling limit of this discrete model, we would expect that the scaling limit also satisfy this domain marker property. So this is why we have this domain marker property here. And the second remark is, in fact, the combination of conformal invariance and domain marker property is very strong. Suppose we have a curve satisfies both conformal invariance and domain marker property. In D from A to B, we run the curve up to a small time epsilon. We define the conformal map phi 1 as the conformal map from the remaining region onto the initial region. Send this tip to A and fix this endpoint B. Then from the conformal invariance and domain marker property, we know that the image of the future part of the curve has the same law as the original curve, and it is independent of what happens in the first step. And so we can repeat the same procedure. We run the curve up to a small time epsilon, define the conformal map from the remaining region onto the initial region. And again, the image of the future part of the curve has the same law as an SLE curve in D from A to B, and it is independent of what happens from the previous two steps. So this tells us if a curve satisfies both conformal invariance and domain marker property, we can explore the curve little by little, and then we get a sequence of IID small pieces. And then, given this sequence of IID pieces, we can map them one by one back into the original region. In this way, we can reconstruct the whole curve. So this tells us if a curve satisfies both conformal invariance and domain Markov property, in order to decide the distribution of the curve, we only need to know the law of the first small pieces. So this implies if a curve satisfies both conformal invariance and domain Markov property, there's not so much choice for the curve because we only need to know the law of the first small pieces. In fact, it is proved that there exists only a one-parameter family, SLE kappa, that satisfies both conformal invariance and domain Markov property. For kappa between 0 and 4, that corresponds to a simple curve, and this is the case we will focus on this talk. So I won't talk about other intervals for the kappa. As I said before, SLE curves are introduced as the candidate for the scaling limit of discrete models. Since their introduction, they have already been proved to be the scaling limit of several discrete models. For example, SLE2 is the scaling limit of loop erased random walk. SLE3 is the scaling limit of the interface in critical Ising model. SLE4 is the scaling limit of the level line of discrete Gaussian free field. So here is the introduction to SLE curve. We can see that when we introduce SLE curve, we try to characterize one single interface in the discrete model. So the next goal is we try to characterize the collection of all interfaces. And when we can go back to this percolation model here again. If we have critical percolation inside this region, and we require all boundary vertex to be white, then we look at the interface of the white and the red. Then we can see that the interface will become loop. There are many loops and they are nested. So the next goal is we want to characterize what's the law of the scaling limit of the collection of all this interface. This introduced to the notion of CLE. So CLE is a random collection of loops in simply connected domain, and it satisfies the following two properties. First, conformal invariance. If we have a collection of loops inside D, phi is a conformal map, then the image of these loops under phi should have the same law as the CLE in phi D. Second, domain Markov property. So suppose we fix some deterministic subset S, and we say that all the loops intersect this S are the loops we discovered. Then for the undiscovered loop, they should have the same law as the CLE in the remaining region. So this is the loop version of domain Markov property. And again, the same as before, this domain Markov property is natural property from discrete models. And another remark is the combination of conformal invariance and domain Markov property is quite strong, and the reason is similar as before. In fact, we can show that there exists only one parameter of simple loops that satisfies both conformal invariance and domain Markov property, and we call it CLE kappa for kappa between A6 and 4. And you can expect that, in fact, in the CLE collection, each loop is an SLE kappa loop. And we also show that, in fact, CLE3 corresponds to the scaling limit of the collection of interfaces in critical Ising model, and CLE4 corresponds to the scaling limit of the collection of level lines of discrete Gaussian free field. Okay, so this is the second object, CLE. The third object is Gaussian free field. I want to start from discrete Gaussian free field. So the discrete Gaussian free field is a measure on functions with density given by this formula. We can also express it in words. So it means we have a discrete lattice. At each vertex, we have a Gaussian random variable. The mean value is 0. And the covariance between two Gaussian random variables is given by the green function for the simple random walk on the region. This is the discrete Gaussian free field with mean 0. Discrete Gaussian free field with mean H partial is just defined as the discrete Gaussian free field with mean 0 plus the harmonic function H partial. So under this law, at each vertex, we still have a Gaussian random variable. And the only difference is the mean value now becomes H partial x. And the covariance is the same as before, it's given by the green function. This is the discrete Gaussian free field. For this discrete Gaussian free field, we can say that it is a pointwise defined random function. So we can smooth this function. So this discrete Gaussian free field can also be willed as a smooth random function defined on the whole region. Next, we let the size of the lattice goes to 0. Then this discrete Gaussian free field will convert to continuous Gaussian free field. But this continuous Gaussian free field is no longer a random function. It can only be willed as a distribution. For this distribution, given any test function rho, each rho corresponds to a Gaussian random variable. Mean value is the integration of each partial against the rho, and the covariance is given by the Green function there. For this continuous Gaussian free field, it also satisfies conformal invariance and domain map property. So now we have introduced the 3 objects. First is SLE, second CLE, and third is Gaussian free field, and all of them satisfies conformal invariance and domain map property. So this explains why there are various interesting relations between the 3 objects. Okay, this is the first part. Then we can go to the second part, the growing mechanism in CLE4. So we have a collection of loops in this unit disk. Now we want to explore this collection of loops little by little, just as the same idea as there. So we draw a small semi-disk of radius epsilon, that's gray one, and we say that all the loops intersect this small semi-disk as the loops we discovered. And if we don't discover the loop contains star ranging, then we map the remaining region onto the unit disk and normalize that arranging. Because of the conformal invariance and domain map property, we know that the image of this collection of loops and to this right-hand side has the same law as a CLE in the unit disk, and it is independent of what we discovered in the first step. So we can repeat the same procedure. We draw a small semi-disk of radius epsilon. We discover the loop intersected, and if we don't discover the loop contains the arranging, we map the remaining region onto the unit disk and normalize that arranging. And again, we get a collection of CLE loops. Yes? I only consider the loops in the simply connected region. Yes. So
the remaining domain might
yes. This is a good question. So they don't need to be. They can be many simply connected domains, and we focus on the one that contains the origin, and map it onto the unit disk and normalize that origin. Yeah. So this is the second step. This is third step. And this is the fourth step. At the fourth step, we discover the loop contains the origin, and we stop. So this is our discrete exploration process of this loop configuration. And here I have a few remarks. So in this discrete exploration, before we discover the loop contains the origin, all the steps are IID. And at each step, suppose we have a probability epsilon to discover the loop. So suppose we have a probability epsilon to discover this loop contains the origin. Because all these steps are IID, we know that the steps big N, when we discover the loop, satisfies geometric law with parameter epsilon. And in particular, epsilon times n will converge to exponential law as epsilon goes to 0. So this is just basic consequence from n satisfies the geometric law. So now what we do is, this is our discrete exploration. At each step, we discover a loop. We may discover many loops, and suppose this is the largest loop we discovered at each step. So L1, L2, L3, Ln is a sequence of loops we discovered from this discrete exploration process, and now we normalize this sequence by its index. So we define gamma epsilon times n equals Ln and gamma t is empty if t is not of this form. So now we have a normalized sequence. This is just a normalized this sequence for the index. And then we can expect that as epsilon goes to 0, this sequence will convert to a boson point process, because all these steps are IID. So this is our discrete exploration, and when let epsilon goes to 0, we can imagine that this discrete exploration will convert to a boson point process. So in this boson point process, the intensity big M should be a bubble measure. So here on this page, I will explain more on what this bubble measure will look like. So recall that this is our one-step exploration. We draw a small semi-disk of radius epsilon. We discover a loop. And we know that in this one step, the probability that we discover a large loop is approximately the same as epsilon to the power beta. And this beta is a function in kappa. And in particular, when kappa equals 4, this beta equals 1. And this is the most important ingredient we will use later in the talk. So now we normalize this probability measure by epsilon to the power minus beta. As epsilon goes to 0, this normalized probability measure will convert to a bubble measure. So it is a bubble, and it is a one root exactly located at x. And this bubble measure is sigma finite infinite measure on bubbles. And just we'll go back to our discrete exploration again. So when in our discrete exploration, we sample this small semi-disk of radius epsilon uniformly over the circle. So now we have to integrate this root over the circle uniformly. And this big M corresponds to the boson the intensity in this boson point process. And the first key claim is when kappa equals 4, this big M is conformally invariant. And the proof only has 2 lines. And you can read it by yourself. And the most important ingredient we use here is this beta equals 1. So there's no exponent then. Okay, I guess you have already read it. So because this is the proof, it's only 2 lines. So the key claim is when kappa equals 4, this big M is conformally invariant. And now we start with a loop of with a collection of loops. We explore a discrete exploration of this collection of loops. We know that as epsilon goes to 0, this discrete exploration will convert to a boson point process with the intensity big M. This big M is an SLE bubble measure, and we know that when kappa equals 4, this bubble measure is conformally invariant. And now we want to reverse the procedure. So given the boson point process, we map this bubble one by one back into the unidisk. And it's principally the reverse procedure in this as I described here. So we map this bubble one by one back into the unidisk. Then we get a sequence from this sequence of bubbles. We get a sequence of loops in the unidisk. And because these bubbles is just get from the CLE loops, so when we map these bubbles back into the unidisk, we can expect that this sequence of loop should have the same law as the loops in the CLE. Okay, so up to now, all the discrete explorations I described are normalized at the origin. And when we map this bubble one by one back into the unidisk, we also choose that our target is the origin. In fact, this origin is not special. We can, for any interior point, we can map the bubble one by one back by target at another interior point. So suppose we can also map the bubble back by target at the interior point Z. So the next question is, what happens if we have 2 target points? So we go back to the discrete exploration. We have a sequence, we have a collection of loops here. We draw a small semi-disk of epsilon, of radius epsilon. We discover the loop intersects this small semi-disk. And now we want to map the remaining region onto the initial region. But since now we have two interior points, we have to choose which point to normalize. So this causes a problem. And the amazing thing here is, because when kappa equals 4, we know that this bubble measure is conformal invariant. It tells us at this step, you can either choose to normalize as Z or normalize as W. There's no difference. It's because of the conformal invariance of the bubble measure. So now we have two interior points. We generate the sequence of loops from the bubbles first by target at Z. And we also have another process of bubbles mapped back into the region, and it corresponds to a sequence of loops target at W. And the previous observation tells us for this two sequence of loops, up to the first time that the two target point are disconnected, the two sequence has the same law. And this is due to the fact that this bubble measure is conformal invariant. Since the two sequence has the same law up to the first disconnecting time, in fact, we can couple these two processes so that up to the first disconnecting time, they are identically the same. And after this disconnecting time, they just evolve towards their target point independently. And we can also use the same procedure to generate process targeted at all interior points at the same time, in such a way that for any two target points, up to the disconnecting time, they're coincident. This is the so-called conformal invariant growing mechanism in CLE4. And all the construction here only works for kappa equals 4, because only when kappa equals 4, we have this conformal invariance. So here is the first result of this talk. So in this result, in this second part, we construct a conformal invariant growing mechanism in CLE4. And in this growing process, we generate a collection of loops, and this loop has the same law as the CLE4. And moreover, for each loop, we have a time parameter. This time is from the bubble measure. So now we have defined a CLE4 with time parameter. The collection of loops has the same law as in CLE4, but one more information we get is each loop now has a time. So if you are lost in the second part, don't worry. You can just remember that we have constructed CLE4 with time. So now each loop has a time, and you still have a chance to understand the latter part of the talk. So now we can turn to the third part. The third part is couplings between Gaussian free field and the CLE4. So I start from the level line of discrete Gaussian free field. So as I said before, a discrete Gaussian free field can just be willed as a smooth random function defined on the region. So now we require this discrete Gaussian free field to have boundary value +1 on R plus and -1 on R minus. Since it is a smooth random function, we can define gamma delta as the level line of this smooth function. As delta goes to 0, this level line will converge in distribution to SLE4. It is a work by Schramm and Sheffield. And we also know that as delta goes to 0, discrete Gaussian free field will convert to continuous Gaussian free field. So it is tempting to say that SLE4 curve is the level line of a continuous Gaussian free field. But here we are not ready to say it, because continuous Gaussian free field is not a function, it's just a distribution. We have to first make sense what do we mean by the level line of a distribution. And then we have to also explain why this random curve is the level line of the field. It's not a level line of the Gaussian free field. So this is the discrete procedure. And now I want to rigorously introduce what happens in the continuous setting. So in the continuous setting, the procedure goes like this. We work in the upper half plane. We first run a simple SLE4 curve from 0 to infinity. So this is a simple curve. it separates the upper half plane into two connected components, left and right. Second step, we sample a Gaussian free field in the left with mean height -1, and a Gaussian free field in the right with mean height +1. And these two Gaussian free fields are sampled in a way that, given the curve, they are conditionally independent. The claim here is the sum of the two Gaussian free fields has the same law as a Gaussian free field in the upper half plane, and the boundary value is the same as the bottom picture here. So in this procedure, we first draw the curve and sample and get a Gaussian free field depend on the information on this curve. And the most surprising thing is, in fact, we can also prove that this curve is a deterministic function of the field. This is very non-trivial from the previous construction, because in the previous construction we first run the curve and we define the field depend on the information of the curve. But finally, we can prove that, in fact, in this coupling, the curve can also be read from the field. And now in the construction of this coupling, we can say that when we sample this curve, we generate the field. This curve behaves like the level line of the Gaussian free field. And later, we can prove that this curve is a deterministic function of the field. And now we are ready to say that this curve is the level line of the field. So this is the setting we make sense of what is the level line of continuous Gaussian free field. And generally, for any fixed real number u, the level line of Gaussian free field with height u is just the level line of h plus u with height 0. And on this page, I will give several basic properties of the level line of continuous Gaussian free field. The first is if we have two starting points, x1, x2, and the gamma 1 is the level line starting from x1 with height u1, gamma 2 is the level line starting from x2 with height u2. If u2 is greater than u1, then this black path will always stay to the left of the red path. This is we can imagine from the discrete version. Next, if u2 equals u1, the two curves will merge upon intersecting. And the third property is the so-called target independent property. So now we have one starting point but two target points. So gamma 1 is the level line starting from x and targeted at y1. Gamma 2 is the level line starting from x targeted at y2, and they have the same height. And the conclusion is the two curves coincide up to the first time that the target points are disconnected. So here are three basic properties from for the level lines of Gaussian free field. And you can guess, in fact, the third picture is the reverse version of the second picture. So in fact, they have the different names and they correspond to different properties of the level lines. But in fact, the third one is just a reverse version of the second one. Basic properties of the level lines. And now we can talk about the couplings between Gaussian free field and the CLE4. Before we talk about the coupling, we have two observations. So we know from the previous introduction, we know that SLE4 curve corresponds to the level line of Gaussian free field. And we know that CLE4 is a collection of SLE4 loops. So we can expect from here that CLE4 should be the collection of the level lines of Gaussian free field. So this should be the collection of level lines of Gaussian free field. So this is the first observation. The second observation is when we construct the level line of the Gaussian free field, we first run a SLE4 curve, And to the left, the mean height is -1. To the right, the mean height is +1. So to the two sides of this curve, there is a height gap of 2. So there is a height gap of 2 to the two sides. So just the two observations from the previous introduction. And now we can state the first coupling between Gaussian free field. So in the first coupling, we first sample a CLE4 loop configuration in the disk. And then for each loop, we sample a Gaussian free field inside the loop. The mean height is +2 or -2 with equal probability 1/2. And all this Gaussian free field is sampled in a way that, given the loop configuration, they are conditionally independent. And the claim here is the sum of all this Gaussian free field has the same law as a Gaussian free field with a 0 boundary value. So in this procedure, we give a coupling between CLE4 loop configuration and Gaussian free field. This is the first coupling between Gaussian free field and CLE4, and is claimed by Miller and Sheffield in 2012 or 10. Okay, 2010. Okay, this is the first coupling, and next is the second coupling. So in the second coupling, this is the part we relate to the second part of the talk. So first, we sample a CLE4 with time parameter. So now we have a collection of loops, and each loop has a time. For each loop, we sample a Gaussian free field inside the loop, but the mean height is 2 minus 2t. And all this Gaussian free field is sampled conditionally independent. And the claim here is the sum of all this Gaussian free field has the same law as a Gaussian free field with boundary value. So this is the second coupling between Gaussian free field and the CLE4, and here we use the time parameter we define on each loop for the CLE4. And I will talk about the idea of how to prove the second coupling. But before that, let us talk about what's the relation between the first coupling and the second coupling. So we recall a standard result about Brownian motion. Suppose Bt is a one-dimensional Brownian motion. We take the absolute value of this Brownian motion, yt. So this yt is the reflected Brownian motion. And we decompose this reflected Brownian motion into countably many Brownian excursions according to 0. And in fact, we know that this Brownian motion, when parameterized by the local time, it is a boson point process of Brownian excursions. So this is, we decompose the Brownian motion to many Brownian excursions. Now we want to reverse the procedure. Given a sequence of Brownian excursions, we want to reconstruct the Brownian motion. There are two ways to this reconstruction. The first way is we first sample IAD coins for each excursion. And we require the excursions positive or minus according to this coin. And then we concatenate all these signed excursions. We know that this has the same law as the Brownian motion. But there is also another way to reconstruct the Brownian motion. So we first concatenate all these positive excursions. So what we get is the reflected Brownian motion. And then we define a local time process for this reflected Brownian motion. And then we know that yt minus lt also has the same law as the Brownian motion. So this is the classical two ways to reconstruct a Brownian motion from a sequence of Brownian excursions. And our two couplings between Gaussian free field and CLE4 are just two counterparts of these two reconstructions. So in the first coupling, inside each loop, the height is +2 or -2 with equal probability. But in the second coupling, the height inside each loop is 2 minus 2t. So here we can also say that our time parameter defined for the CLE4 has the same role as the local time process for the Brownian motion. So this is the relation between the first coupling and the second coupling. And now we can talk about the idea how to prove this second coupling. So recall that this is our discrete exploration of a CLE4 loop configuration. And the idea of the proof for the second coupling is very similar to this discrete exploration. So now what we want to do is we want to explore a Gaussian free field. we start with a Gaussian free field with mean height 0. We draw a level line of certain height, and this level line will decompose this unit disk into several simply connected regions. Some of the region has height minus epsilon, and another region has mean height 2 lambda minus epsilon. So if we discover the origin, we stop. But if not, we map the connected component that contains the origin onto the unit disk and normalize at their origin. Because of the conformal invariance and dynamic property of Gaussian free field, we know that the image of the field there under this conformal map to the right is still a Gaussian free field. And the only difference is the mean height now become minus epsilon. So we can repeat the same procedure, but the only difference is we are lowered by 1 epsilon here. So we run the exploration process of this Gaussian free field. If we discover the origin, we stop. If we not, we map the connected component contains the origin onto the unit disk and normalize at the origin. And now everything is the same as before. It's still a Gaussian free field, but the mean height becomes minus 2 epsilon. This is the third step, and this is the fourth step. At the fourth step, we discover the point origin. And here, when we discover the point origin, we can see that the mean height of the field at this step is 2 minus epsilon times n, and this big N is the step we used to discover the point. And the same as again, this big N just satisfies the geometric law, but it satisfies the geometric law, but with parameter epsilon over 2. So as epsilon goes to 0, we know that this mean height will convert to 2 minus 2t, and this t is an exponential law. And if you still remember how we explore the CLE for loops in the discrete exploration, you can see that as epsilon goes to 0, this t is exactly corresponds to the time parameter we defined for the CLE for loop. So this is the idea of the proof. So this is the second coupling. In the second coupling, inside each loop, the field has a mean height 2 minus 2t. And this t is exactly the same as the time parameter we defined for the CLE4. Okay, here are several natural questions. The first question is, when we construct the CLE4 with time parameter, in fact, we construct the loops and the times at the same time. The natural question is whether the time parameter is a deterministic function of the loop configuration. Because in the construction, we don't know whether it is true, because we construct them at the same time, and we don't know whether the time parameter can be wholly decided by the loop configuration. If the answer to this question is yes, then this time parameter would give a conformal invariant distance on the loops on CLE4. This is a very interesting object because it is totally conformal invariant. And the third natural question is, in fact, we can also introduce CLE kappa for kappa greater than 4. And in that case, the loops can touch each other. So we can define a natural graph distance on this when kappa is greater than 4. And the question is, suppose we consider CLE4 plus epsilon. As epsilon goes to 0, we normalize this graph distance. Whether this normalized graph distance will convert to the time parameter we define on the CLE4. And this is the main topic of the first talk in this afternoon. Okay, thanks for your attention. And here I enclose several references in case you are interested in the detail of the proof.
Questions? Comments?
Could you give some precision in your second coupling? What is exactly the red curve you?
What?
In the second coupling you explained.
Mm-hmm.
What exactly is this red curve? How do you build it?
The red curve.
The red curve that is flow line on the GF.
Yeah. Okay, so here. From the basic properties of the level line of Gaussian free field, in fact, we can generate a level line starting from any boundary point targeted at any other target point, and with any height you want. But some of the height will give a curve, but some other height will go out of the region, and you stop at the starting point. So suppose you have a height. The height is, in fact, it is -1 plus epsilon. So you have 0 boundary Gaussian free field. You consider the level line of this height. Then the level line will look like this. It will be very close to the boundary where epsilon is small. And suppose you are targeted at this point. And if you also have another target point, as I said before, it is target independent. So up to the first disconnecting time, the two curves coincide exactly. So after we suppose here is the origin, we run the curve first target at the y1. After some time, this y1 will be disconnected from the origin, and we stop. And we know that up to this time, you target at the y1 or target at another independent or at another target point. It doesn't matter. So now we choose another target point y2, and we'll continue this curve. And again, at some time, this curve will disconnect y2 from 0, and we choose another target point. So we can also choose a target point to be here. And finally, what we get is, at some point, this curve will hit the continuation threshold, and it can't continue anymore. And we stop here. Because of the conformal invariance, we know that this procedure doesn't depend on the sequence we choose the target point. And because we also know that the two curves starting from the different points will merge some point, so in fact, if we only consider the boundary here, this boundary also doesn't depend on the starting point. So this is what we call the discrete exploration of Gaussian free field with size epsilon.
Questions? So, I have a question. So you have this infinite measure capital M in your process. Are there descriptions of this measure? Or?
Yes. For this bubble measure, you are inside the upper half plane, and it is rooted at the origin. So it is a bubble. And what we know the relation between SLE curve, the real SLE curve, is that if we follow the curve after some time, given this part of the curve, the law of the future part of the curve has the same law as the portal SLE from here to here, under this bubble law. So this is the precise relation between this bubble law and the chordal SLE.
Okay, so thank the speaker again.